Okay, good afternoon. Sorry, good morning.
Good afternoon, sir.
Today we'll see flow measurement introduction. Now, flow measurement means what? Already you have studied that in your second year in fluid mechanics subject. That is, we are going to measure the flow by using venturimeter, orifice meter, and pitot tube. Therefore, flow measurements are essential in many applications, such as transportation of solids as slurries, compressed natural gas in pipelines, water and gas supply systems to domestic consumers, irrigation systems, and a number of industrial process control systems. The types of flows encountered in the measurements may be any one or combination of the following types: clean or dirty, opaque, wet or dry, hazardous, corrosive or safe, single phase, two phase or multi-phase, laminar or transitional or turbulent. Pressure may vary from vacuums to high pressures of many atmospheres. Temperature may vary from cryogenic levels to hundreds of centigrades. Flow rate may be of minuscule type, that is few drops per minute, or massive type involving thousands of liters per minute. Please mute your mic. Mhm. Okay, this is nothing but flow rate. The selection of a particular flow measuring equipment depends primarily on the nature of the metered fluid and the demands of the associated plant. For example, an aircraft fuel meter requires to be compact and must not be affected by the changes in orientation, but has to handle only a clean and non-corrosive fluid. On the other hand, many industrial flow meters have to work with fluids which may be corrosive in nature or may contain foreign matters, but the equipment may be relatively large and of fixed type. Additionally, the other factors that govern the choice of a particular flow metering device are the various performance parameters like range, accuracy, repeatability, linearity, dynamic response, type of output like analog, digital, etc. Further, another requirement may be to indicate or record the rate of flow, total flow, or maybe both these quantities. Flow measuring devices generally fall into one of the two categories, namely primary devices or quantity meters and secondary devices known as rate meters. The distinction between the two is based on the character of the sensing element that interacts with the fluid flow. The output of the sensing element is then suitably modified so as to indicate or record measured values. Quantity measurements by mass or volume are usually accomplished by counting successive isolated portions, whereas rate measurements are inferred from effects of flow rates on pressure, force, heat transfer, flow area, etc. It is quite often possible to obtain the rate of flow from a quantity meter by a suitable choice of modifying elements. Further, it is important to note that the quantity meters are generally used for the calibration of rate meters. Now, first flow measuring device we will see, that is positive displacement meters. The term positive displacement meter is applied to a flow measuring device so designed that the metered fluid is repeatedly filled and emptied from a space of known volume. The principle of this measurement is that the liquid flows through a meter and moves the measuring element that seals the measuring chamber into a series of measuring compartments, each holding a definite volume. Each element is successively filled from the flow at the inlet and emptied at the outlet of the meter. In other words, we could say that positive displacement meters chop the flow into pieces of known size and then count the number of pieces. Positive displacement meters are widely used in low flow rate metering applications where high accuracy and repeatability under steady flow conditions are required. Further, they are easy to install and maintain and have moderate cost. These types of meters are generally used by the water and oil undertakings for accounting purposes. However, since there are moving parts in these devices, the wear of the components may alter the accuracy. Therefore, these instruments need calibration adjustment over an interval of time. Another limitation of such meters is their suitability to clean fluids only. Further, these devices are generally flow totalizers and do not give instantaneous rate of flow. In most positive displacement meters, the transduction of the flow takes place in the form of rotary motion. In short, we can say that these meters are hydraulic or pneumatic motors whose cycles of motion are recorded by some form of a counter. Energy is extracted from the flow to drive these meters, resulting in a pressure loss in the fluid system whose flow is being metered. But the energy required is extremely small, just enough to overcome the friction of the system. Some of the commonly used devices of this type are as follows. Therefore, first is the nutating disc meter. See that diagram has been shown. This is the nutating disc meter. It consists of this, first of all, casing. Here inlet is there. Here outlet is there. Now outlet is completely closed. This is the drive shaft to counter mechanism. When water is going to, or any liquid or any fluid will enter here, and if you will drive this shaft, then what will happen? This horizontal plate is there. It is going to be horizontal and water will flow from this side to that side or to the outlet side. Therefore, the nutating disc meter shown schematically in figure 5.22 consists of an eccentrically mounted disc which nutates or ovals in the metering chamber which has spherical sides. The liquid enters the left side of the meter alternately above and below the disc, forcing it to rock in a circular path while rotating about its own axis. Thus, the liquid from the inlet causes the disc to nutate before it goes to the outlet. Means what? What is happening? When the liquid will enter, this disc is going to nutate or it will start rotating about its own axis. Or that motion is also known as oval motion. Oval means that may be eccentric type of motion. Thus, the liquid from the inlet causes the disc to nutate before it goes to the outlet. Further, the viscosity of the liquid ensures both sealing and lubrication. A small spindle attached to the sphere traces a circular path and is used to drive the mechanical or electronic counter, which can be calibrated in terms of liquid discharge. This type of flow meter has simple and rugged construction, low pressure drop, low cost, and a good accuracy of the order of plus minus 1%. It can be used to meter wide variety of liquids. Moreover, it finds a wide application as domestic water meter. Next is the sliding vane type meter. Therefore, see that this is the inlet. Again, because of this, when This rotor will revolve. Then these vanes are there. These vanes, because of this here vortex or this vortex will be formed and this water will come through this outlet. This type of meter has an accurately machined body having a rotor with 4 evenly spaced slots, which form the guides for the vanes. The metered liquid entering the inlet revolves the rotor and the vanes around the cam, causing the vanes to move radially. The vane nearest to the inlet port begins to move outwards and becomes fully extended at point A, shown in figure. The vane ahead at point B is already fully extended, and thus a measuring chamber of known volume is formed between the two vanes and the meter body. A continuous series of chambers at the rate of 4 per revolution are formed, which deliver the flow at the outlet. This type of meter has low pressure drop and can give an accuracy of the order of plus minus 0.2% of the measured values. An important application of sliding vane type meter is its use as positive displacement pump, which can cause the flow rate and measure it simultaneously. Such a pump is routinely used for dispensing petrol, diesel, or compressed natural gas in the fuel filling stations. Next is the lobed impeller meter. Therefore, this is the lobed impeller meter. When this water will come or enter through the inlet, these lobes will rotate and these lobes will force this water to the outlet, and water will come through the outlet pipe. Therefore, we'll see the theory. This type of meter consists of two rotors mounted on separate parallel shafts. The rotors are lobed and revolve in opposite directions in a closed fitting chamber. The rotor lobes have cycloidal and involute shape, which ensures accurate matting. The incoming fluid is trapped between the two rotors and is conveyed to the outlet as a result of the rotation of the rotors. For every rotation of each rotor, the swept volume corresponding to twice the area A, shown in figure, is passed through the meter. Thus, the number of revolutions of the rotor gives an indication of the volumetric flow. Since the speed of rotation is proportional to the volume flow rate, the rate of flow display can also be obtained by monitoring the speed of rotation of one of the rotor shafts. The rotations of the lobed impellers can be monitored by magnetic or photoelectric pickup. The frequency of the output is proportional to the flow rate, and the electronic integrating circuit gives the totalized flow. Alternatively, the rotations of the lobed impeller are counted by connecting them to mechanical registers. Meters of this type are available for pressures up to 60 atmosphere for the flow rates ranging from 10 to 10,000 meter cube per hour. Within these flow rates, the meters have an accuracy of plus minus 1% over a range of 10 to 100% of the rated capacity. Further, these meters have low pressure drop of the order of 50 mm of Hg at the rated capacity. The limitation of the instrument is that it is relatively expensive because for obtaining accurate results, the clearances between the rotors and the casing as well as between the rotors have to be made very fine. Further, these close tolerance levels restrict the meter to clean fluid applications like metering of gas flows and refined petroleum products. Therefore, this is lobed impeller meter. Now, special methods. We'll see these special methods and then we'll stop. There are certain flow measuring devices that cannot be strictly categorized as fluid mechanical types or primary flow measuring devices of the indirect type of rate flow meters. Therefore, these are discussed as special type devices where principle of operation is generally non-fluid mechanical in nature. For example, ultrasonic time delay technique, electromagnetic effects of fluid flows, heat transfer from heated wires, Doppler frequency shift of scattered light, etc. are some of the principles used in the measurement of fluid flow parameters. Ultrasonic flow meters. The operating principle of this type of instrument is based on the apparent change in the velocity of propagation of sound pressure pulses in a fluid with a change in velocity of the fluid flow. In practice, we employ short bursts of sinusoidal pressure pulse whose frequency is above the audio frequency range, that is above 20,000 Hz. A typical frequency may be of the order of 10 megahertz, that is 10 raised to 6 Hz. Here 7 has been written, sorry. The following are the advantages of an ultrasonic flow meter. First, offers negligible resistance to the metered fluid system. Second, has a reasonably good accuracy of the order of plus minus 2% of the full scale value. Third, has a linear relationship between the velocity and the output. Fourth, is suitable for both liquids and gases. And fifth, since the output is electrical, the readout can easily be either analog or digital. Because of the above mentioned advantages, the device finds special applications, namely measurement of ocean currents, then vessel spread water, fog, etc. See that this is the ultrasonic flow meter. Figure A indicates travel time difference method, that is single transmitter receiver system. Transmitter single receiver here. Travel time difference method with twin transmitter receiver system. And here oscillating loop method. Now next is the electromagnetic flow meter. See that this is the electromagnetic flow meter. This is the pipe. This is the permanent magnet. Therefore, electricity is supplied. This is the electrode. Therefore, this magnetic flux lines will flow from north pole to south pole. This is the fluid motion. Therefore, electromagnetic flow meter rate of flow may be determined for electrically conducting fluids by measuring the EMF induced across the fluid stream when it passes through the magnetic field. This technique cannot be used for electrically non-conducting fluids like gases. However, it gives quite satisfactory results for fluids with as low conductivity as water. The principle of operation of the unit is directly analogous to Faraday's law of electromagnetic induction for solid conductors. The law states that whenever a conductor cuts lines of magnetic field, an induced EMF is generated, and the magnitude of this EMF is proportional to the rate at which these lines are cut, and the EMF is perpendicular to the plane of conductor and the magnetic field. The direction of the induced EMF is given by the Fleming's right hand rule. The construction of the electromagnetic flow meter consists of the following. First, a permanent magnet or an electromagnetic magnet, which may be either AC or DC, around a non-conducting pipe. Two electrodes placed at right angles to the magnetic field for picking up the induced EMF. Third, fluid flow in the pipe, which is at right angles to the plane of magnetic flux lines, and the induced EMF direction, which is along the line joining the electrodes. Now for the conducting fluid flows, the induced voltage E naught generated according to Faraday's laws is E naught is equal to PLV into 10 raised to minus 8 volts, where B is equal to magnetic flux density, L length of the conduction, V velocity of the conductor. Therefore, this is the electromagnetic flow meter, Fleming's right hand rule. The effective length of the conductor corresponds to the inner diameter of the pipe, and the velocity of the conductor is proportional to the mean flow velocity. The volume flow rate of the circular pipe is given by Q is equal to pi by 4 T square V. E naught is equal to 4 BQ into 10 raised to minus 8 divided by pi d volts. This shows that the volume flow rate Q is directly proportional to the induced EMF E naught as long as the flux density remains constant. The EMF is measured by means of two electrodes built into the non-magnetic length of pipe. Further, these electrodes are made to be completely flush with the inner surface so that they do not obstruct the flow and at the same time are in direct contact with the flowing fluid. Unfortunately, the EMF generated by the instrument is very small, that is typically of the order of 1 millivolt for a fluid velocity of 1 meter per second, and the resistance of the fluid is often very high. Therefore, the output of the instrument is generally amplified suitably. In the practical equipment, alternating magnetic field is usually preferred. The main reason is that it prevents polarization of the electrodes, that is, collection of gas bubbles on the electrodes due to electrolytic action, which form the insulating pockets in the vicinity of the electrodes. The main advantage of the electromagnetic flow meter is that it causes no obstruction in the flow line of the meter fluid. This makes it particularly suitable for fluids containing solid matter. Further, the device is quite accurate and has a wider linear range with good transient response. That is why this instrument is widely used for metering corrosive acids, cement slurries, sewage, paper pulp, detergents, greasy and sticky fluids, etc. However, these meters are expensive and their use is limited to the fluids having conductivity at least of the order of 4 into 10 raised to minus 6 ohm per centimeter. Therefore, this is the end of the flow measurement. Now we will start next chapter.